Hello, my name is Barry Evans, and this is my second CS 490 senior seminar talk. So this time it's shading again. So shading part 2. This time I'm going to go a little bit deeper into like the actual mechanics of shading and kind of show the like baseline shading techniques. I wanted to get into like physically based rendering and modern stuff, but as I was writing the presentation, I figured this will take up plenty of time just kind of doing the basics. So before we get into any of the actual code or theory, I wanted to go back to my last presentation and kind of refresh. So if you remember, there are two types of rendering. There's rasterization, or there's ray tracing, and there's rasterization. Ray tracing is used in movies like over here in Avatar. Rasterization is drawing triangles, and that's used in video games. It's real time. We're going to be looking at rasterization, basic rasterization shading. So how that works is you've got some object, and this is some camera, so your camera field of view, and that object gets projected down onto this image plane, which is essentially the screen. So then each of these squares are pixels, and the GPU basically figures out where like which of these pixels need to be shaded based on where the object gets placed on the plane. It picks those pixels, and then a shader is run. So that's what we're going to be looking at today is actually writing the shader and talking about the theory behind how to get something to look like it's being lit. So to remind, a shader is a relatively small program that runs on the GPU, runs once per pixel on the screen. It takes in information about the geometry, and it outputs a color to the screen. So it just takes in like the direction that things are facing and stuff like that, and you can do some calculation and spit out a color. And here is that basic shader that I showed. This is doing diffuse lighting, and I'm actually going to explain what's going on here really soon. And we're basically going to be making this diffuse shader, and I'm going to be using Unity game engine for that because it's just really quick to start, and we can just start programming with it. So with that, we kind of recovered the basics. So let's go ahead and look at some of the theory behind it. So all right. So generally, when we're talking about shading, there are two types of lighting. There's diffuse. Excuse my handwriting. Diffuse lighting, and there is specular lighting. So diffuse lighting is this. So if you've got a surface that you're trying to shade, there are some basic things that we know about it. Arguably the most important is the normal. So the normal is just the direction that surface is facing. So if I had a sphere, oh goodness, excuse my drawing abilities. Good enough. At this point, the normal is this way. And at this point, the normal is this way. So that's what a normal is. So in this case, we have a flat plane, and this is our normal. So another important component to shading, obviously, is the light. So in our case, we're going to assume we've got a directional light. So it's a light like the sun that's just going straight down one direction. So we know that there is some direction that the light's coming from, and that's this vector. This is L for light direction. So we've got the direction of the light, we've got our normal. So what diffuse light is, when you see an object that's like very rough, like concrete or like rubber, anything that's not shiny, that's got a lot of diffuse light. So when light hits an object, a percent of that light is scattered in a random direction. So when I have light that hits the surface, the light will go off in every different direction. And that's a diffuse light. And the way that we can calculate diffuse light is with this this equation. Hope you are sort of brushed up on your linear algebra. So if each of these are represented as 3D vectors, so we've got some xyz pointing toward the direction of the normal, some xyz pointing from the light, in the direction of the light. Essentially, we're just trying to figure out how much light is being hit by this point. So actually, let me back up. Let me give an intuition for this. So let's use a circle again, if I can pull off a circle. Goodness gracious. All right. Okay, so if we have our light coming from this way, we can assume that on this side of the sphere, no light is hitting it. From this side of the sphere, there's no light hitting it. And right here, where the light points to the sphere most directly, where these two point to each other most directly, this is going to be the brightest point. And going out from there, it's just going to fall off. So it's going to get darker as it goes back until on the back side there's no light, and up here it's the brightest. So the way we do that is we can take this light vector and this normal vector, and this is like the most basic calculation in lighting that you could know. So your outgoing light is equal to the dot product between your normal and the opposite of your light direction. So essentially, because your light is going toward your surface, you want to be comparing, so like take this for example. When you do the dot product, you want to be comparing your vectors like this, getting the angle between them, and that's going to tell you how much light is hitting that point. So that's why we invert, instead of the light coming this way, we invert the vector going this way so that we can get the angle. So this is it. This is what makes things pretty much look reasonably lit. So that's diffuse lighting. So to reiterate, diffuse lighting is a percentage of light that comes and hits the surface and scatters in a completely random direction. And that will make it look like a rough surface, like rubber or like concrete or something like that. And this is the calculation to do it. We dot the normal with the light direction, and we do that because we want the angle between the light and the normal. That angle between the light and the normal will tell us how much the light is hitting the surface. That's diffuse lighting. That one's a little bit tougher to grasp. Specular lighting is a little bit easier to understand. So with specular lighting is essentially shininess. So this is like when you see something shiny and you move your head, the reflection kind of moves. It's just reflected light. So if we've got that same, So if we've got that same surface, and this time, instead of the light bouncing off in all directions, what specular light is is light bouncing off in a reflected direction. So this light that's coming from our light source is going and hitting the surface, and then it's bouncing off in a very specific direction. If you remember from physics, it's just the direction in is the direction out. So it's bouncing, it's doing a perfect reflection off of our surface across the normal. So this is specular light. So the bouncing is specular light. But there's one more thing we have to take into account when we're calculating specular light, and that's the view direction. So this is basically, with specular light, we're trying to calculate, okay, so let me compare it to diffuse. In diffuse light, we're trying to compare how similar the light vector is with a normal vector. In specular light, we're trying to calculate how similar the reflected light direction is. We'll call this R. We're trying to calculate how similar the reflected light direction is with the view direction. So say we are viewing the reflected vector from this position. So we've got our view vector that we can call V. And our specular light is just the similarity between V and R. So if we were to write some pseudocode for this, the first thing we want to do, let's break it down into parts. The first thing we want to do is reflect L across N. So reflect L across N. So, and then that's gonna give us R. And so now we have R, and then remember our goal is to compare how close R is to V. So our light out is going to equal, just like before, we're dotting R and minus V, because we want these vectors, just like before, if this is our reflected vector R, we want to get the angle between these, so we use negative V to have them face both the same direction and get that angle. Otherwise we're going to get an opposite value than we want. So then this is our light out. This is it. This is the specular light. So we just reflect across the normal, and then we dot with the view direction. And this this specific formulation of specular light is called the Phong model. There are actually a lot of different formulations for specular light and diffuse light. This is just the most simple one that's the easiest to explain. But when you get into physically based rendering and more advanced lighting, these become quite complicated. But for the sake of understanding, this is kind of the baseline lighting that you'll see in a lot of older games. So now we can go ahead and implement it. So I'll open up Unity. And so this is kind of what it's going to look like at the end. We've got, if you move the camera around, you can see the light moving with it, and you can see if I move the light in my scene over here on the left, you can see the light moves around the object, and you can see the two components. The component that kind of fades off, you can see it's the brightest where the light is facing it, and it kind of fades off to black. And then the specular light, you can see is that hot spot. And when I move my camera, you can see that the specular light moves like a reflection. And that view direction is our camera. If you look at the diffuse light is not dependent on our view direction. There's no V in here, which means when I move my camera, it stays the same, right? That gradient from black to very bright stays the same. But the specular light is dependent on the view direction. So when I move my camera, that specular highlight also moves. So, all right, so let's get into the shader. I'm just gonna make a new, all right, give me a second, let me set this up. Okay, back. So here we have a blank shader. It's just black right now. It's just spitting out the color black. And in our scene, we've got the shader ball, which is just a little form that lets us see what our shading's looking like, a sphere and a plane. So, like I mentioned before, this is Unity Game Engine. Just makes things quick for us. So here's what the code looks like. It's kind of intimidating at first, but it's I'm gonna omit some stuff, not talk about some stuff, so that we can just focus on the shading. But essentially, there are two shaders here. Actually, there's the vertex shader and the fragment shader, also called the pixel shader. So the fragment shader is the one I talked about earlier. It's this guy where it runs once for each pixel on the screen. So this is where the actual math will happen. And then there's the vertex shader. So how 3D models work, they're a collection of points, so they're a collection of positions connected up into triangles. And each of those positions can have a little extra data associated with them. So each point has a normal associated with it, and that normal is just a 3D vector that is like the one that I explained in the math. So we'll be using that 3D vector in our calculations here. So what the vertex data does is it figures out where the vertex will lie on the screen, and then it passes all the information for each pixel on to the pixel shader, so the pixel shader can do the math and actually put it on the screen. So we're not going to worry about the math here. All you really need to know is it's finding out where the pixel needs to go on the screen, and then it's getting the normal from that vertex, and then it's passing it. This return is passing it down to this vertex shader. Essentially, it's giving us the normal, and the vertex position, and that's all we really need. So a couple more things. I went ahead and there are kind of some special Unity syntax to get the view direction. So that was our V here, the way the camera's facing, and the light direction, which we use in both the specular and diffuse. So there's some special syntax to get those in Unity. So I just went ahead and did it. You just have to know that this is our view direction and this is our light direction, and that's it. And then the last thing that might look kind of weird here is the float 4, float 3 thing. As you can kind of guess, it's just a 3 or 4 dimensional vector of floats. So this one holds 4 floats, this one holds 3 floats. That's it. So what the shader is actually doing is, right now it's just getting our view and light direction, and then it's outputting black to the screen. We output a float 4 because we have our RGB value, and then we have our alpha value, which is basically like transparency, but we don't have any transparency, so we're just setting it to 1, which is not transparent at all. And that will output something like this, black. So it's working. Okay, so now we can start transferring the math from our blackboard here into the shader. So so the first thing is let's do the diffuse light. So this is going to give us basic lighting so we can see what's going on in our scene. So if you remember, we need to figure out what our normal is, and we need to figure out what our light direction is. So what I'm going to do is I'm going to make another float 3. So this is a 3D vector that's going to represent our normal. And this, like I said, the vertex shader passes data to the fragment shader. So what I'm doing here is this V2F is the data that's coming from vertex v to the fragment f. So, and that holds the normal. So I can say I.normal, and that will give us our normal. And like I said, I already set up the light direction. This light direction is mapped to the light in our scene. Where's the light? This light in our scene. So whichever way this light is facing, that's the direction that we're getting in here in light direction. So now we've got our normal, we've got our light direction. Now all there is to do for our diffuse lighting is get our diffuse value. So we just need to dot the normal in the opposite of the light direction. So Unity will already do the negating for you. So this light direction is actually facing away from our normal like this down here. So all we have to do is, so this is going to give us back a float because it's a dot product. So a dot product between two vectors will just give you a like a normalized version of the angle. So it's just going to be a float, and we'll call this diffuse light, and that's going to be equal to the dot product between the normal and the light direction. So like I said, they already negate the light direction for you, so normal dot light direction should give us our diffuse light. Now what we can do is, instead of passing zeros, the black, we can pass our diffuse light. So if you set all the RGB to be the same value, you're going to get some value of gray. So if we set these all to be our RGB, when we recompile, we get an error. Let's see what we did wrong. It's probably a typo. Oh, I forgot the comma. There we go. And there's our diffuse lighting. Simple as that. If you are astute and you know your 3D math pretty well, you might realize that when we do the dot product between this normal and this light direction, if we have a normal that's facing the opposite direction of the light direction, then we're going to get a negative value. And colors are never negative, so that's bad. In fact, if I take the absolute value of this, you'll see what I mean. Some of the values are negative, so when I do absolute value and flip it to a positive, you will see that the back side of these over here are lit, which they should not be. They should be black. So what we can do is say diffuse light equals the max value between 0 and diffuse light. So if my diffuse light is negative at all, it's going to say, what's bigger, a negative value or 0? And it's going to give us back 0 into our diffuse light. So now that should be fixed. So cool. Now we've got legitimate diffuse lighting, and it matches up with the math that we talked about. So I guess it's working. Okay. Diffuse light. Now we can go ahead and talk about specular light. So this one was a little bit more complicated. Like I mentioned, diffuse light is some percentage of light that bounces randomly. Specular light is the other percentage of light that bounces in a predictable direction. When you add them together, you get the full light at the surface. So once we're done with our specular light, we can just add them and we should see something kind of cool. Sirens. Okay, so specular light. So we have our pseudocode here, and it's actually pretty close to the HLSL code. We've got our light direction, we've got our normal. All we need to do is calculate this reflected direction, and we have our view direction. So let's start with this first step. We want to reflect the light across the normal to get R. So light bounces across the normal, we get R. And it's actually really easy to do that in HLSL. We don't need to do any crazy reflection calculation we can actually use a function called reflect. This is the normal input, and this is the vector that needs to be reflected across it, which was our light direction. And this gives us our R. Simple as that. So now that we have R, all we have to do to get our final specular light is take the dot product between our reflected vector and our view direction to see how much light actually hits the eye. And we should have our Phong shading. So remember, this is called Phong shading. Actually, we'll call this specular light. And then, so we take the dot product between our reflected light, and this is actually a vector, so I'll call it reflected light dir for direction. And then we want to dot it with our opposite view direction, right? Because again, we want them to be facing the same direction to get the angle between them. So the exact same thing's going to happen like we saw with the backside of the diffuse light if we don't clamp this. So we can use the exact same math. Max between 0 and specular light. So it just make sure it doesn't go below 0. And now if we output this, assuming all of the math was right, there we go. This is our specular light. It looks a lot like the diffuse light right now, but if we move our camera, we can see the light does move with the camera. So I'll go over this one more time. So we reflect our direction across the normal, our light direction across the normal to get our reflected light direction. And then we dot our reflected light direction with the view direction to see how much light is facing the eye. And then we just make sure it doesn't go below 0. So right now it's kind of wide. This is just how the Phong shading works. If we want a tighter, almost like a shinier reflection, we've got to do, we have to raise our reflection to a power. So if we go pow, let's say something big like 20 of specular. So this is our specular light to the 20th power. So if you think about, this is some value from 0 to 1. Because we do our dot product, we get some value from -1 to 1. We clamp that. Now we have a value from 0 to 1. When we raise that to a power, that's gonna like squeeze our range. So that gives us something like this, which that is way better. That's more like a shiny reflection thing going on. It's pretty cool. And if we move our light, we can see it's dependent on the light direction, and it's dependent on the view direction. See that? So now the last step is to add our light together. So we have our final light. Let's just make that a float, and we'll call it final light. Final lighting is equal to the diffuse light plus a specular light. If now we replace that as our output, our final light should give us both of them together. So now we've got our diffuse light with our specular highlight on top. So I want to make that highlight even tighter. Yeah, there we go. That's pretty much all I wanted to show in this talk. Is like the basic lighting. That's how it works. It gets a lot more complicated, a lot more theory that goes into like how these surfaces are actually constructed out of like very tiny mirrors and some weird crazy black magic like that. And I wanted to get into that in this talk, but it kind of is a lot of information to get across just the basic stuff. So hopefully I will be able to talk about that in my lightning talk. So thank you for watching this, and please give me a good grade.